Greetings and welcome to the first module on mathematical modeling. Today we will be exploring how to conduct a bivariate regression using Excel's trendline function, as well as better understand the R-square value that the trendline function produces. The success criteria for today's lesson will be for students to be able to use Excel to create a scatter plot graph, perform a regression using the trendline function to find the best fit curve, as well as to calculate and interpret the R-square value. To give regression some context, let's think about it in terms of a problem. How do I empirically model the relationship between a set of input variables to a set of its output variables? For example, how can I use mid-year exam results to predict the end-of-year results for a class of students? To create a scatter plot graph, we need to highlight two columns of data with the x variable on our left and the y variable, which will be our output, on the right. Next, we click on the Insert tab and we select Scatter. This will give us a scatter plot of the exam results. The x-axis will represent the input variable, which can also be called the explanatory variable or the predictors, whereas the y-axis will give us the output, which will be our dependence variable, or also known as the predicted variable. Now, personally, I do not like to use dots for my scatter plot. So if you want to change it, what you do is that you right-click on the dots. This will open up an option to format the data series. You click on Format Data Series and you'll give you some series options. Next, you select Fill in Line, Marker, and you can change the marker options to built-in type. And here I selected the cross to represent each of my points. Now I add my trend line by right-clicking on the crosses, and this will open up a tab that allows me to add the trend line. This will open up options for formatting your trend line. Make sure you click on Display Equations on Chart and Display R-squared value on chart. The default regression is a linear model. In this case, our best fit line is given by the straight line equation y equals to 1.12x plus 16.2. This equation represents our mathematical model that could possibly predict or estimate future students' end-of-year results given their mid-year results. The value 1.12 is our regression coefficient. This is the gradient of our straight line graph. It estimates that for every one more mark that a student scores for their mid-year exam, they are on average going to score 1.12 more marks for their end-of-year exams. However, it need not be a linear regression. We could always regress a data to an exponential function. What is important is your rationale. Perhaps you think that students experience a positive feedback loop in their studies. Perhaps students who did well in their mid-year exams will be more motivated to do even better for their year-end exams. You could consider an exponential regression to model such a flywheel effect. Or perhaps in your research, you've uncovered that there's some form of diminishing returns to students' effort in their mid-year exams. So you could try to fit the curve against a logarithmic one. Or you could possibly fit it against other polynomials such as the cubic function or power functions, as long as you have a good reason why. Lastly, let's look at the R-square value. This number is also known as the coefficient of determination, and it gives you a rough measurement of the goodness of fit, which is how well your best fit line predicts the available data. In the best case scenario, an R-square value of 1 would mean that all the little crosses lie on your best fit line and your equation perfectly predicts the output given an input. This is incredibly unlikely, as in most research, there should be other hidden factors at play. Now let's look at the mathematics that goes behind the computation of the R-square value. Let's say we have a small data set represented by these 4 red circles. We know their output variable, y1 to y4. We can average all the output to give us y bar, the mean. Next, we calculate the deviation from the mean, shown by these 4 blue dashed lines. Then we will square these 4 blue lines to give us 4 blue areas. And we add up these 4 areas to give us the total sum of squares, or SS total. Going back to the 4 original points, we can plot our regression line. Let's call it y equals to fx. And next we want to find the deviation from our prediction. So this is shown by this golden dashed line. This will tell us how far each of the points deviates from the predicted values. Next, we square these 4 lengths, and this will give us 4 yellow areas, these squares. When we add them up, we will get the residual sum of squares. To calculate the R square, we'll just take 1 minus the SS residual divided by the SS total. Some last thoughts on R square values. Firstly, that if you experience an R square value that is less than or equals to 0, this could imply that you have a problem in your data, perhaps a massive outlier, or you could be using the incorrect model, or perhaps there's no relationship between your X and Y variables. Second is that a good R square value usually depends on your field of study. Certain studies like engineering, which calls for more precision, might have a lower tolerance for what is a good value. Lastly, a bigger R square value isn't always better. A high R square could be the result of an overly complicated model. What you need to do is test the reliability of your model using a new set of data. We've come to the end of the first module for mathematical modeling. Stay tuned to the next topic where we'll be exploring multiple variate regression using Excel and looking at the p-values and the f-test that comes together with it. Thank you and have a good day of learning.